This is the 2020 scholarship exam, question 2. Right. For a moving source of sound, the frequency heard by the stationary observer can be calculated using the following equation. We've just got the Doppler equation. Explain the use of the plus or minus symbol in this equation. So the plus or minus symbol is for when it's the source is, when the source is moving towards or away from the observer. And that's literally it. If it's going towards the observer, you'd use the minus because you'd expect a higher frequency, and if it's going away from the observer, you would use a, towards, you'd use a minus, and then away you'd use a plus. Right, I'll pause it and write it up. Right, so literally just said plus or minus used when the source is moving towards or away from the observer, plus for moving away, minus for moving towards. Sweet. State the assumptions made about the velocity of the moving source. So it's got to be moving at a constant velocity, and it's got to be moving directly towards or directly away from the observer. Otherwise, you've got to use trigonometry. So I'll just pause and write that. Cool. There's no need to really read that out because I just said it. Right, what do we got? Next question. And an object is moving in a circle with a radius r at a constant speed vs. So that's the speed that it's moving around the circle, and this is the radius of the circle, while emitting a sound with a constant frequency. At an instant, the observer at point P, or at the instant, the observer at point P hears the sound at maximum frequency. The source has reached the position indicated on the diagram. Show that theta equals this, whatever that is, plus whatever that is. So there's a few things to note with this. First and foremost, to figure out exactly where the sound would have occurred, we basically get the person, we get our ruler, and we just go up to the face of the circle, because that is when it would have made, that would have been when it's directly, so you can see this vector is pointing off to the side, so the sound wouldn't be coming directly towards P. It would only be coming directly towards P at that point about here. So then what we'll do is we'll put a straight line into the center of the circle. There we go. We notice that this is a right angle. I don't know what I'll call this. I think I'll call this D2. The answers split the theta into, so just like a few things I should probably straight off the bat. Using dimensional analysis, this could either be in degrees or probably radians, because whatever, radians. So this, the only two like sort of formulas for angles are the trigonometric formulas. So like this, sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, and tan equals opposite over adjacent. Or you've got theta is equal to d over r, or it's equal to angular velocity times time. So they're the only formulas you can really use. So you can probably look at this and be like, wow, I can probably see that this is definitely using the trigonometric formulas. So it's using some ratio in here. And you can see that if, I know that the formula used, we call the answers used A and B, so I might as well just use, I use what I used when I calculated it. I think I split this into, I call this Kronecker Delta, how do I do it? Kronecker Delta, and I called that phi. And I know that, what do we got? Theta is equal to phi plus Kronecker Delta. These are just like common Greek letters that you can use. And what can we see? So here, theta, this, not theta, phi. So this is, I better say that is phi, and that is Kronecker Delta. I think it's Kronecker Delta. Right, so I can see, I just lost my train of thought. I can see that this here is using the trigonometric functions, and it's either phi or Kronecker Delta. And I can pretty much see that here we have, this here is r, from here to here. And I can see that this angle here, this is 90 degrees. So this phi, its co-interior angle, or whatever you call it, or this minus 90 degrees would give you this angle right in here, which would mean this angle over here is thigh. I hope you can sort of follow. So I know that this plus whatever this whole angle is adds to 90. So it must mean this angle in here from there to the horizontal is the co-interior, so it should add to 90 with that one there. So basically what we can say is now we have thigh and we have D and we know what the radius is from here to here, that's just R. So we can say that thigh is equal to sine theta, sine inverse I should say, sine inverse opposite over hypotenuse, which is equal to sine inverse, what is the opposite? The opposite is R over D. Okay, sweet, so we've already shown that part. Now what we need to do is think, well, how do we figure out this Kronecker delta, this one in here, which is stupid messy. I should just push this out to the side. That is that. How do we figure that out? Well, we know when the sound was emitted, it moved a bit. And we've already used the first, we've used one of the functions. The next sort of function that we could probably use is we could use d over r, but we've already sort of got that in here. And we can see it's moved. So if it's moved, we need to use the moving formula. So we're going to say that this distance that it's traveled from here to here is going to be, so I'll just chuck down here, the distance that it's traveled is going to be equal to the angular velocity that it was traveling times time. But we know that the angular velocity is just the linear velocity, Vs, divided by the radius, because we've got the formula angular velocity was just V over R. And we're going to times that by time. Cool. But the time for the wave to get from that point to here, so that time is equal to the distance it traveled. So I call that distance d2. So d2 over the velocity it was traveling, which is the velocity of the wave, vw. And that d2 is equal to, so this would be, I don't know, like the smaller side of a triangle. We've got one side, we've got the hypotenuse, so it's going to be equal to square root the hypotenuse, which is from Pythagoras' theorem, minus r squared, still divided by the velocity of the wave. And now you can sort of see where I've gone with this. So thus that angle from here to here, is equal to Vs over r times square root d squared minus r squared over Vw, and then you can sort of see that theta is equal to the sum thigh plus Kronecker delta, which is equal to sine inverse r over d plus Vs square root d squared minus r squared over Vwr. So this just takes a bit of playing around with. Oh, damn, I can't see that. It takes a bit of playing around with, and knowing that this has to be in the units of degrees, or degrees of like radians. It's an angle, it has to be in the same units. So you're looking for formulas with similar units, right? Yeah, but annoyed that this is just all this blank stuff over here. I think if you had this actual booklet, this would sort of fold out over, but whatever, I can fit in another page. Right, so we have the Doppler effect can be observed when a moving observer approaches a stationary wave source at speed VO. The relationship for the frequency when an observer moving at speed approaches a stationary source is given by this formula here. Explain when the observer would experience a greater Doppler shift. When the source approaches the stationary observer at speed v, or when the observer approaches the stationary source at speed v. I mean, the same speed. Right, so the way to think about this question is, I've got all this space up here. You write the other, so I'll write the other formula, f dash is equal to, was it f vw, and we're approaching the source. Yeah, we're totally approaching the source. Vw minus Vs. Sheesh, my brain is scattered today. Right, That is totally it. And we can just look at the formula. So what happens when you get really, really, really close, or basically when you approach, like you approach the wave speed. So here you can see this is for when the source is moving. If the velocity of the wave, if the source gets the velocity of the wave, the bottom or the denominator approaches 0. So essentially your frequency approaches infinity. In a nutshell, I mean, it's not going to approach infinity, it just becomes undefined, because you sort of lose what the idea of a frequency even is. And then the other, like the converse, so when the observer is approaching the wave, you add these two together, even if these were two exactly the same. So if the wave is equal to this, like the velocity of the source, so like you're moving towards the, what do you call it? You're moving towards the source, you'll just get 2 VW. So you just end up with twice the frequency. So now you can basically, you've got the answer. You could draw it pictorially. So if you like visually think about it, if you're running towards the source, even if you're going the speed of sound, you would only get through twice as many waves. So normally you'd only get through one set of waves. Now you're going like the same speed as a wave source. You'd only get through 2 sets of waves. Whereas if you're actually the source moving, you're catching up to the waves that you're emitting. And essentially you break the sound barrier and you get an indefined frequency, right? So I'll pause it and write out the full answer. And then I'll try and discuss it. Right, so I said the greatest shift occurs when the source approaches the observer. We basically just discussed this. This is because when the source moves, its relative velocity with respect to the wave is velocity of the wave minus the source, which equals v relative. This comes to a point where v relative approaches 0 and f dash approaches infinity. So with this formula here, and you get infinite frequency, or just really, really high frequency just before then. However, this is not true when the observer moves towards the source, as you get the two things adding together to equal 2 VW. So when when the velocity of the source approaches, when the observer velocity, this should just be the observer velocity, approaches the wave speed, it gives 2 times the frequency. And I just put an example of an infinite frequency is a shock wave given off by an object traveling at supersonic speeds. Another example of infinite frequency is if you hit, well, it's not infinite frequency, it's undefined. So I should really change this to undefined. I can't be bothered. Just cross it out, and you know it's undefined. If you pluck it, or if you hit a drum, if you whack it and then just hold the drum, so you only hear one beat, you don't get you can't say it has a frequency, because frequency is cycles per second. And if you haven't got more than one cycle, you don't know how many, what its average would be. There's a great video by 60 Symbols. Professor Moriarty goes over, I think, what is frequency. I'll try and link it in the description. I'll try and link it in the description, and I'll link in, there's an awesome simulator that covers this. Basically you can see how this works. You can move the source, and you can move the object, and you can see what happens for both cases.